All right, so ladies and gentlemen, let's launch into projectiles. Projectiles are things that fly through the air under only the influence of the force of gravity. Now, you might say, well, how does it get flying through the air? Of course, there's a force to get it going. Like in the guy over here shooting his basketball, okay, he's giving the initial force. That's the guy from flipping physics. But after he pushes it, it's flying through the air. The only thing acting on it is the force of gravity. Or we can look at the Angry Birds down here, right? The Angry Bird, once he is released from the slingshot, only the force of gravity is pulling him down. His inertia or his momentum is carrying him forwards. And then we look at this example with the plane dropping the crate, what that might look like. And you can see that this little crate here is going to follow a curvy or projectile path. So when we say projectile, what we mean is something that flies through the air under only the influence of the force of gravity. So let's take a look at a couple of places that we've been, and let's see how the physics that we already know informs us about the physics that we're about to explore further, which is projectiles. Now, when something is flying through the air, if I chuck something up in the air, it's going to be moving, but it's going to be moving up and then come back down, but it's also going to be moving left to right. And so we're going to define this as horizontal, or the X direction, and we can look at the vertical or the Y direction. And we've done this for the first part of our year together. So just a quick recap on some of these problems. Here's how we would solve them. A sprinter runs the 100-meter dash in 10 seconds. What was his average velocity in meters per second? So what we would do here is we would say, well, our distance or displacement in this case, 100 meters. Our time was 10 seconds. And if it says what's his velocity, we would use the equation to solve for velocity. Go figure. That would be 100 meters in 10 seconds, or 10 meters per second would be his average velocity. Very quick, very easy. The distance from Philly to New York is 100 miles at an average speed of 40 miles per hour. How long will it take to get from one city to the other? How long? That's solving for time. So we're going to use this equation. Time is delta x over v. Now we always want to write our list of knowns. So our delta x here is 100 miles, and our v is 40 miles per hour. And so if I plug those in, we'll get 100 miles over 40 miles per hour. And I should be able to do that mental math, but it's early and I don't feel like it, so I'm going to put it in my calculator. Yeah, of course. It's 2.5 hours is how long it would take. And then if it takes you 2 hours to make a trip at 35 miles per hour, how far is that trip? How far is going to be solving for delta x, which is given by vt. So we got to make sure we have our variable straight over here. 35 miles per hour is our v, and our t is 2 hours. So we plug these guys in. 35 miles per hour, and the time is 2 hours. Multiply those two together, and you get 70. It looks like how far is the trip? 70 miles is going to be our trip distance. Okay, so there's a quick little recap of some of the types of problems we've seen, and we call this constant motion, right? You notice there's no acceleration in any of these problems. We're going at a constant speed. And so I want you to keep this idea in mind. As we move left to right, we are going at a constant speed. I'll tell you more about why that is in a minute. Let's look at a few of the falling type problems that we've seen. We know that if I toss something up in the air, it's going to come back down, and it's going to constantly accelerate at a rate of g, or 9.8 meters per second squared. Whether it's on the way up or on the way down, it's always going to be accelerating downward. So here we go. Upton Chuck is riding something. He free falls for 3.5 seconds. What will be the final velocity, and how far will he fall? All right, so we always know that g is 9.8 meters per second squared, and it looks like it's asking us for what will be the final velocity. Well, vf equals vi plus gt. Just a quick little reminder, v is velocity, of course, f means final, and I means initial, all right, at the beginning of the problem. Now, it does say they free fall, and it says you are getting dropped, and if you're getting dropped, your initial speed is 0, aka you're falling from rest. So we can plug that one in, and then we can plug in our negative 9.8 meters per second squared times 3.5 seconds, and we can calculate how fast we're going. Now, the reason we have the negative is because we're moving down, right? And so our velocity does include direction, so negative 34.3 meters per second would be how fast we're going at the end. But we also are asked to find how far will he fall. Well, how far distance in the vertical direction is indicated as delta y. And now for my students, this might look like a funky new equation. It's really not though. Okay, if you look at this guy, we've seen y equals 1/2 gt squared. Now if you consider falling from rest, your initial velocity is 0, and 0 times t is 0, so this whole term just disappears. That's the correct equation though if we ever have a situation where we are moving at the beginning of a problem. So let's go ahead and plug this in. 1/2, we got g, negative 9.8. We have t, which is 3.5. And be careful here, you're only squaring the time. So be careful, I'm gonna do that first. I'm gonna do 3.5 squared, and then I'm gonna multiply by 9.8, and then I'm gonna multiply by 1/2. And it looks like we are going to fall a distance of 60.0 meters. So there's your two answers for the first part. All right, we'll do one more just to show you time. A feather is dropped from a height of 1.4 meters. Height is going to be y. Y is how high. That's 1.4 meters. And it says determine the time for the feather to fall. So time is square root of 2 times 1.4 meters over 9.8. And, oops, I love when it skips ahead. I really don't. Okay, 2 times 1.4 divided by 9.8. That's going to be the square root of that. Oops, sorry. I'm trying to go too fast. 2 times 1.4 divided by 9.8. Don't rush a good thing, guys. Oh, my Lord. Square root of the answer. Nope. There we go. Get rid of all this extra garbage here. Okay, let's try it one more time. Boom. Don't want to get this wrong because I'll be really confused doing it at home. 0.53, that's why you got to bring your own calculator, by the way. Don't trust the answer that you're given. Is that one, okay? So the next one says a baseball is popped straight up into the air and has a hang time of 6.25 seconds. Determine the height to which the ball rises before it reaches its peak. The time to rise to the peak is 1/2 of the total time. I think what it means is how high does the ball go? Yeah, okay. So if the hang time is 6.25 seconds, we've discussed this in a previous unit, is the time it takes to go up is the same time, is equal to the time it takes to come back down. So if the whole trip, all the way up and all the way down, was 6.25, the time it takes to get to the top is exactly half of that. So the time we're looking at here to get to the top is 3.125. And so when it says how high, delta y is how high, we have 1/2 gt squared plus v initial t. Now our v initial, we do have one, but check this out. We can define this as our starting point because we know that up there, the v initial is 0. Pretty convenient, huh? And if we do that, then that term goes away. Well, you would notice that, and we're ready to go, okay? Because we have 1/2, and then the g is 9.8, and the t is going to be our 3.125. That gets squared. And the height that we are going to fall or rise, whichever you want to call it, because guess what? It's symmetrical, is going to be 47.9 meters. So that's the height, or how high we go. Now, Mr. Simpkins, we already learned this stuff. Why are we doing this again? This is why. Because keep in mind that when things go up, they come back down in the y direction. We know that's a very predictable thing. And we also know that horizontally in the x direction, things move at a constant motion. Unless, of course, you're in a car accelerating. But let's consider this example. If I shoot something, if I shoot this cannon off of a cliff, all right, if I just throw something, let's say we can turn gravity off. All right, so we're turning gravity off. This is fun. We're violating the laws of physics in physics class. Go figure. And so the blue objects here are showing how this thing would move if there's no air resistance and no gravity. Let's say we go to space and we shoot a space cannon. All right. Well, once I push something, it's going to move at a constant speed. Now, we haven't gotten into forces yet, but just think of it this way. If I'm at rest, I have no reason to accelerate. If somebody pushes me, I'm going to accelerate. But if somebody takes me to an ice rink and pushes me across the ice and there's very little friction, I'm going to keep moving. An object in motion stays in motion unless acted on by an outside force. I'm going to keep moving unless something stops me. And so as this cannon fires, you notice that the horizontal motion is evenly spaced. And if you remember Hansel and Gretel, our friends from the first unit, if the dot diagram is evenly spaced, that is showing us that we are moving at a constant speed. So let's summarize this in your table on your notes. In the x, or horizontal direction, after every second, the object moves the same distance. Why? Because we're moving at a constant speed. In fact, the object's velocity is constant. This is in the x direction, the horizontal direction. And the object acceleration is 0. You only accelerate if there's an unbalanced force. There is no unbalanced force once you leave the cannon, right? Of course, the cannon exerts a force, but once you're flying through the air, there's no more horizontal forces acting on you, so there's no reason to accelerate horizontally. Let's look at the y direction. Well, imagine the part of the motion where if I just took a cannonball and dropped it off of a cliff. Oh, we're familiar with these. We know that you're going to move a little bit and then a little more and a little more and a little more and a little more and a little more every second. Just like Hansel and Gretel, if we saw these breadcrumbs that were starting to grow in their spacing or be spaced further apart, that would indicate something is gaining speed or accelerating. All right, so on the way up, the object's velocity is slowing down. That's not in this picture, but if we toss something in the air, would not its velocity slow down? On the way up, slow, 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 and then on the way back down, it would speed up. After every second, the object moves. Well, if I toss something up in the air, we know it's going to be moving fast. You guys did this this assignment last week. It's going to be moving fast, but then it's going to slow down. And if it's slowing down, we're going to cover less distance each second. So every second, the object moves less distance on the way up, and every second on the way down, the object is covering a greater distance. All right, and of course the object's acceleration, well, anything in free fall, we know the acceleration is 9.8 meters per second squared, or negative 9.8 meters per second squared, and it's constant acceleration, okay? So horizontally, all right, we have constant velocity, and vertically, we have downward acceleration. So these are the two big ideas that we want to keep in mind. Now, how does this all tie together? Well, we started with doing these problems. So anytime you're looking at a projectile and you want to analyze its motion or make a prediction or figure out where something's going to land, you're going to be using these very simple, straightforward equations. Why are they simple? Because there's no acceleration. Why is there no acceleration? Because there's no horizontal force once you leave wherever you started from, right? So that's why we travel with a constant velocity in the horizontal direction. And then as far as the vertical piece goes, we recapped some of these free fall and toss-up problems, because if we are dropping or tossing something, then we are going to experience a downward acceleration due to that unbalanced force of gravity. Remember, we said there's no reason to accelerate if there's no force. Well, in the vertical direction, there is a force. It's the force of gravity. And so these are the big ideas that if we can get these in our minds right now, okay, I toss something through the air. As it's moving, its horizontal velocity is going to stay the same, and its vertical velocity is always going to be changing. If you can keep those two ideas in mind, and they're very straightforward, basic, logical ideas, right? If you can remember those two things, this unit is going to go very well for you. All right, so that is our introduction to projectiles. Tune in next time for a few samples and a few simulations for how projectiles fly through the air. It's Mr. Simpkins here in the Simpkins Physics Corner.